Uh, my name is Francesco Cantaboni, and today I'm here to present you my work about the production and characterization of lattice samples with solid shell in 74 pH stainless steel by laser powder bed fusion technology. So various alloy can be applied with this technology, in particular titanium or cobalt alloy, and also stainless steel and more others. The powder metal was used with this machine, and there is a source of energy, in this case a laser, that melts the powder locally and layer by layer fabricate the 3D component, as you know. In this case, the production of metal structure, we decide to use the stainless steel 17.4 pH, and for its good weldability, for excellent corrosion resistance, for the microstructure characterized by austenite and martensite, and also for the combination to high tensile strength and high toughness. This kind of technology is good also and perfect to build the complex geometry such as lattice structure. The lattice structure, in fact, is an interesting solution for several fields: aerospace, biomedical, mechanical, and so on, due to its excellent properties, in particular for the lightweight, height strength and stiffness, heat dissipation, and social absorption. But the lattice will be insert in a solid component, and the key point of my work is to study the interaction between the lattice part and solid part. So I want to understand what happened at the interface between these two different dense parts. Let's start to see the technology. We use the ProHex 100 by 3D system, and we use the process parameter that you can see here in the first table. In particular, we set the power to 100 watts and a scanning speed of 300 millimeter per second. And another important thing is the building chamber that we inflate with nitrogen. This is really important for the inert atmosphere, not only for the oxidation, but also for the microstructure of a build component, because it's not the unique gas that we can use with this kind of technology. And the chemical composition of the powers is also reported here in the second table. For the design of the sample, we decided to print a basic geometry, such as square-based sample with a length of 22 millimeter and a height of 20 millimeter, and with a shell thickness of 1 millimeter for the solid part. Instead, for the lattice part, we applied a unit cell, FCC unit cell of 5 millimeters cube on volume, connected with cylindrical strut and with a node connection spherical in shape. After that, we analyze in particular the microstructure and the defects of heat-treated samples and as-built sample. The treatment was conducted and performed by the solution treatment plus aging treatment. And after that, we perform also the compression test to understand the mechanical characteristic of this element. The goal, as I said before, was to understand which is the role of the shell on the mechanical behavior and eventual critical issue on the interface due to the connection with the lattice part to the solid part. Let's start to understand what happened with this interaction. And so we said at the beginning, after the production of the sample, to see which is the critical issue. In particular, it can be noted here the presence of porosity and also here, but also in particular is important to see that we don't have a perfect spherical node here, but we have a sort of distortion of the geometry. But this is normal because we pass from a low size of the strut to higher dimension of the solid shell. After this first analysis, we performed also the heat treatment. The treatment is conducted with started with a solution treatment with T1 at 1030 degrees for 1 hour, and followed by aging treatment at T2 at 480 degrees for 4 hours. This is conducted in argon atmosphere, also the cooling, just to don't have to allow to avoid the oxidation of the sample as possible. The main features for the solution was for the recrystallization and homogenization of the microstructure, as is widely explained in literature. and aging also for the formation of strengthening precipitates, in particular for the containing of copper precipitates. The main aim of the treatment was, in fact, to have a strength and hardness increase. So let's start with the analysis of the microstructure. At the beginning, we can see in the longitudinal and cross-section of the samples, we etched with the fry reagent for 30 seconds, and we can detect in the longitudinal cross-section, in particular with the white arrows, the typical melt pool overlapped for the process due to the laser energy that melted the powder locally. After that, in the transversal cross-section, we can see the scan track of the laser, and they ask to us the path of the laser that occur during the processes, and is indicated with the yellow arrows, while with the red arrows, we can see the columnar grazing section. After the heat treatment, we obtain another kind of microstructure. In fact, the primary microstructure with melt pool and scan track disappear and occur the precipitates that we can find along the grain boundaries and also inside of the matrix. More deeply, we decide to study this kind of microstructure to understand which components are inside. And in the first picture for the as-built, we can see three main zones, and we can detect a grain in AB1 and a copper segregation in AB2 and the melt pool in AB3. The most important thing or what I want to focus you is the copper segregation, because in particular we found this big area and is deposited on the bottom on the melt pool. This copper segregation is rich in copper. In fact, it presents 24% of copper. And thanks to the heat treatment, this segregation solubilizes and promotes the nucleation of the copper. In fact, we can find in the second picture a copper-rich precipitates. We analyze, for example, in one precipitate in the surface, and we found an higher amount of copper. In fact, we detect a 36% more or less the presence of the copper. Moreover, the presence of nitrogen, as I said before, as an austenite stabilizing element likely allowed the formation of austenite, which is partially transformed into martensite during rapid solidification cooling. And now we performed also the XRD analysis to understand which phase are present. At the end, I performed also the mechanical characterization. So we performed some compression test on the as-built and heat-treated sample, free for each kind of sample. At the beginning, we can appreciate it that the two different curves present some different characterization, because for the as-built we have a lower value of stress, and it is present a sort of plateau when it reaches the peak of stress. While for the heat treatment, we obtain a higher strength, of course, and not a plateau, but a decrease in strength. But the very important things in this study was the deformation, because in this case, we obtain a deformation of the shell that follow the compression. So we don't obtain a detachment of the shell like I obtained in another study for the titanium sample, as you can see in this picture, because here we applied the same compression test, but we obtained that the lattice, the internal structure, expanded to the external direction, and detach the solid shell from the structure. Instead, in the case of 17 pH, we obtain a deformation of the shell. And so we understand that we can use the 17 pH with higher load and, for example, this titanium to lower load, and for different application. For example, 17 pH is probably used, it can be probably used for shock absorption. Moreover, I also detected the hardness of the component. So we performed some micro Vickers hardness to understand if effectively we have an increase of hardness. And in fact, we detected an augmented in the hardness for the heat-treated sample. This is probably due to the transformation of the microstructure, and also for the presence of precipitates. Moreover, I also collected some results and mechanical results about the young modulus, yield strength, and the strength, ultimate strength, and we found an augmented of the resistance and also to the hardness. At the end of this work, I concluded with some consideration, and the fabrication atmosphere nitrogen, as I said before, is a good austenite stabilizing, and so influence the microstructure for a built sample, generating the copper segregation rich of copper, as I said before. The grain recrystallization occurred during the heat treatment, as well as strength and hardness increase, and the formation of strengthening precipitate containing copper. And from the compression test, the defects were detected on the interface, such as the porosity and geometrical size, in particular for the node and close to the connection between the two different dense parts. And the critical issue was detected at the interface, but not enough to detach the shell from the internal lattice. So, as I said before, we can obtain a good variation of the shell that follow the compression and the deformation. The detachment of the shell from the inner lattice part was not occurred, and the shell follows the collapse of the internal lattice structure. Typical of this material, as I said before, and in another study that I presented for the titanium-based alloy. The possible application of 17 for pH lattice structure for intact absorption for the typical and classical deformation of the shell that we can see. And the future activity that I want to perform to understand the behavior also of the lattice in this alloy, but without a solid part, is analysis of the lattice without solid shell to understand what happened, and to perform the XRD analysis to understand if maybe there is more austenite or martensite on the on the surface of the samples. Thank you for your attention. That's it.
Thank you for your presentation. We have time for one question. Okay.
Thank you for your presentation. I'm just wondering, have you performed the CT scan for all the samples you have printed?
We
to
want
evaluate the geometrical deviations, something like that.
We want to perform also this CT scan, but we can't do it again at the moment. So it's a work in progress because it's a wide work and we have to perform it also.
Okay, so I thought it would be interesting to see how the deviation occurred, especially for the lattice region
Yes.
in the middle.
Thank you.